In this video, we will discuss force components of an object on an inclined plane. So if you ever put a book or a box or any object on an inclined plane, you may have observed that the object slides down to the bottom. And through this diagram, I will show the force components that causes this sliding motion. So over here, we have a box on an inclined plane, and assuming that this box is on Earth, we can say that this box is going to experience the downward force of gravity. And we can say that this equals the mass of our object times gravity. Now, we cannot say that the normal force is counteracting the force of gravity because remember, the normal force is perpendicular to the surface the object is on. So what we can do is break up our force of gravity into its vertical and horizontal components. So we can break it up into its component that is perpendicular to our surface, and we can call this our force of gravity that's perpendicular. And we can break it up into a component that is parallel to our surface. And we'll call this the force of gravity that is parallel to our surface. Now that we broke up our gravity vector into components that is perpendicular and parallel to our surface, let's look back at our inclined plane. Well, remembering from geometry, if we have a right angle, then these two other angles must equal 90 degrees. So we can say that this angle over here is 90 minus theta. And we also notice that this line and this line over here are parallel to each other. So we can use the alternate interior theorem to say that this angle is equivalent to this angle over here, which again is 90 minus theta. Now you may be wondering, what is this angle equal to? Well, remember, we're assuming that our force of gravity is perpendicular to our surface. So this over here is 90 degrees. And knowing that these two angles have to equal 90 degrees, we can say that this angle is equal to theta. Now we can shift this component down over here, and you should see that we create a right triangle when we do so. And we can use our basic trigonometry principles to find the magnitude of the force perpendicular to the surface and the force parallel to the surface. And we can see that the sine of our angle is equal to the magnitude of our parallel force of gravity divided by our original gravitational force, which equals our mass times our gravity. And we see that the cosine of our angle is equal to the magnitude of our perpendicular force of gravity divided by our original gravity, which is our mass times our acceleration. And we can multiply each side by the mass of the object times the gravity to get that the magnitude of the force of gravity that is parallel to the surface equals to the mass of the object times gravity times sine of theta. And we get that the magnitude of the force of gravity that is perpendicular to the surface is equal to the mass of the object times gravity times cosine of theta. And now we have two formulas that help us determine how much force due to gravity is being pushed into the ramp and how much force is allowing the object accelerate down the ramp. Now, let's look at some problems. In this problem, we have a box that is elevated 30 degrees, and we are asked to find the magnitude of the normal force. Well, like we did in the lecture, we know that this box is going to experience a downward force of gravity. And we want to break up this vector into components that is perpendicular to the surface and parallel to the surface. So in regards to the problem, we know that the normal force is the contact force that is perpendicular to the surface. And the normal force must equal the force of gravity that's perpendicular to the surface because we are assuming that our box is not accelerating down into the ramp. So we have that the magnitude of the force of gravity that's perpendicular to the surface is equal to the magnitude of the force of gravity. And guys, I realized I made a mistake. These are not the given formulas that we derived earlier. And remembering the formula that we derived earlier in the lecture, we know that the magnitude of the gravity that's perpendicular to the surface is equal to the force of gravity times cosine of theta, and that equals our normal force. We also know that we can rewrite our force of gravity as the mass of the object times the gravity. So you have mass times gravity times cosine of theta equals the magnitude of our normal force. Now we can plug in our values. We know that the mass of the object is 6 kilograms. And we know that the gravitational pull on the Earth is 9.8 meters per second squared. Times cosine of our angle. And the angle that we're referring to is not necessarily this one, but this angle over here, which so happens to be equivalent to the angle of our elevation. So we have cosine of 30 degrees equals the magnitude of our normal force. And we get that the magnitude of our normal force is approximately 50.92 newtons. Now let's look at another problem. Once again, we have a box on an inclined plane, but this time we are asked to find the magnitude of the box's acceleration. Well, like we did before, let's draw the forces that are being acted on our box. So we have that the force of gravity is acting on our box. And we must break up the gravitational force into components that is perpendicular to our surface and parallel to our surface. So in regards to the problem, we are asked to find the box's acceleration. So we must look at the parallel component of our force of gravity. In a previous video, we said that Newton's second law states that the force is equal to the mass of an object times its acceleration. So using this principle, we can say that the magnitude of the force of gravity that is parallel to the surface is equal to the mass of the object times the acceleration in the parallel direction. And before we move on, I forgot to mention that the mass of our object is 4 kilograms. So now that we have this equation, we can replace the magnitude of our gravity in the parallel direction with the force of gravity times sine of theta. And this is going to equal the mass of the object times the acceleration in the parallel direction. And we know that the force of gravity equals the mass of an object times gravity. So we can simplify this left-hand side to our mass times gravity times sine of theta equals the mass times the acceleration in the parallel direction. And by dividing each side by our mass, we get that our acceleration in the parallel direction equals gravity times sine of theta. Looking back at the problem, we can plug in our values to get our acceleration. So we have that our acceleration in the parallel direction equals gravity, which we know is 9.8 meters per second squared, times sine of theta, and we know that our angle is 60 degrees. But remember, the angle that we're referring to is this angle over here, which is 60 degrees. So we multiply our gravity by sine of 60 degrees to get that the acceleration in the parallel direction equals 8.49 meters per second squared. So in recap, we learned that the magnitude of our force of gravity that is perpendicular to the surface is equal to the force of gravity times cosine of theta. We also learned that the magnitude of our force of gravity that is parallel to the surface is equal to the force of gravity times sine of theta. And over here, I redrew the diagram from earlier in the lecture. Thank you for watching this video and hope to see you next time.